Thank you for the introduction. It's a pleasure to be here after all these years. The last time I was here was for a machine learning summer school 2 years ago, and I think the talk I gave at the time was perceived a bit negatively. I was, trying to explain that, when you try to apply machine learning in real life, it's not like what you do in research. And people understood it as, don't forget all the research, just go to engineering. So I'll try to, compensate for that a bit and still say a few nice words about machine learning research. So let me start with the story. How many of you guys have seen this movie? And you were not even born. So, no surprise that you haven't seen it. For those who haven't seen it, so it came out, I was like 8, and it was the first movie I saw with computers in it. And, I think I watched it like maybe 100 times. I loved it. There was this cool kid who, gets a computer and knows how to hack into computer system remotely with a modem. What a modem is. But so this guy, he manages to penetrate the Pentagon computer system, and he bumps into some computer which happens to be an AI, right? And this AI is talking to him and all that. And the thing is that this AI was programmed by some guy called Professor Falken, and who is like an AI expert, and he managed to figure out how to program computers so that they learn how to play strategy games on their own, right? By playing against each other, or at least the computer is playing against itself and learning how to play tic-tac-toe or chess or checkers and all this. And I was really fascinated. And at the time, 1983, that was complete science fiction, right? At the time, there was no, of course, there were people working on that, maybe some remote corner of academia, but it was not possible to imagine that someone would do that for real, especially at a time where personal computers even barely exist. Anyway, after seeing that movie, I decided this is my goal in life. I want to be Professor Falken. I did not quite manage, and if you look at the history, I kind of failed to join the AlphaGo group. But still, so I mean, one thing that is important is, okay, so it started like 34 years ago, you could say, with this movie. 1992, there was this first success of really a learned computer program that plays a strategy game like backgammon. Then, of course, you have heard about Deep Blue. It's not quite learning, so it's not quite machine learning. So that's why maybe I should. Exactly, yeah. IBM is not happy. Deep blue screen. Thanks. All right. What you may not know is that the guy who is giving the TensorFlow tutorial with me is actually a rock star in this field, because he developed the first computer program that managed to beat a professional Go player. That's called Mogo. And the AlphaGo team is very jealous that. Anyway, but that's the story. But why am I saying all that? Because really, one thing that you may not realize, because you're so young, right, is that this thing that started as science fiction 34 years ago, or much before that, and which was a science, right? Like when I did my PhD, it was kind of an esoteric topic within computer science, but still it was a science, machine learning. But it's now, evolving before our eyes into a full-fledged engineering discipline. So that's something that happens, once in a lifetime. That's the field that you're working on as a research scientist becomes, a full-blown engineering field. And you come, I'm a bit jealous of you because you come at the exact right time, and a bit too old to kind of fully benefit from that explosion. But what are the implications of that? The fact that this is becoming something mainstream, and now we call machine learning as one field, but think of computer science, right? Computer science is way more than one field. You can't have a a computer science summer school. Doesn't even make sense. So I'm suspecting that in 10 years, machine learning summer school would not even mean anything, right? Because it will be, like 10 different subdisciplines at least, right? And so the point is, there is a boom in terms of everything related to machine learning, from the tools to the software to the hardware. It's like a new way of programming computers, and that means there are lots of implications throughout all the industry. Another point is that there are lots of applications, and just like the fact that you're working on this scientific field is now very connected to the application. So that means it's very easy to do something scientific and advance the state of the art in science, and at the same time having direct application on real application, on real problems, which is very encouraging. And another observation is that you will see, I'm suspecting that the ratio of people that use machine learning in their everyday life, or that are engineers working with machine learning, the ratio of scientists will change dramatically. That doesn't mean that there won't be machine learning scientists anymore, but at least there will be a lot more machine learning engineers than we are seeing now. And just to give you an idea of how serious this is becoming, this is what we call the TPU, a TPU pod, this thing here. What it is dedicated hardware for machine learning specific, so for running deep learning style computation. And the magnitude of that is fascinating, right? Like this one pod contains 64 TPUs. TPU is a chip that is designed to do certain computation. It's kind of a super specialized GPU, if you will. And these 64 TPUs deliver 11.5 petaflops, so whatever, 10 to the 15 floating point operations per second. That's kind of crazy. How crazy is that? Is that if you take, I think, like if you take 1,000 such GPUs together, which is actually what Google is making available for free to researchers around the world, 1,000 of them is like delivers more, more computing power than the top #1 supercomputer. So that means, we already have available for science the top supercomputer specifically for deep learning, and that's just the beginning. So be prepared for the explosion. But now let's talk more about what are the challenges in research associated with that. You probably have seen such curves recently. So this is the error rate of the best machine learning system on ImageNet. So it's an image classification data set. And you see over the years, this has decreased to go below the human level of accuracy. At the same time, this is the number of layers in the best neural network. The number of layers has grown quite a bit. And the question is, like, why is it that finally we managed to have some systems that keep improving at a very fast pace? There are multiple reasons to that. One is the increase of availability of power that was saying before, right? Now we have, like, the Moore law is over, right? That I guess. It's very hard to cram more transistors onto one chip. But what it has been replaced by is dedicated hardware and putting together lots of them, lots of chips together in a very tightly connected network. That allows to deliver still more power. There are lots of tricks to make these things converge, right? You may have heard some of them. And there has been also a large exploration of all possible architectures, mostly by PhD students. The fact that the pool of PhD students is increasing makes this exploration even more large scale. And the one specific aspect of it is that we have seen that, like, replacing feature engineering in the sense of, like, before we were crafting for this kind of image problem, different kind of features from knowledge of how images behave in some sense. And now we're stacking, like, if you stack more layers, you can get it for free. You don't have to worry about how to design your features, just work. And so, in some sense, we can say that, like, if we look at this curve, supervised learning or supervised classification is essentially solved to a large extent. But so then a natural trend is to say, well, if that's solved, let's look at more complex problems. Let's attack other problems, and especially if we can cast those more complex problems into the same framework, then we can apply this big hammer that we have, like this deep learning hammer, and it will work. You have heard from Max Wellingstoke that there is this DPFI operator, which is like take any conditional probability distribution in your model, replace it by the deep neural network. I would go even further and say that take any problem. If you can cast it as a supervised learning problem, throw a deep learning system at it, and you'll solve your problem. One such example is when you move from classification to complex outputs, meaning instead of just a 0-1 output or a multi-class output, you have something structured. One particular example is sequences. Sequences are fairly tricky to model, and the trick that has been used in the recent years is to use a parametric model in the form of a deep learning network to model the distribution over sequences on the output. Right? So you have a generative probabilistic model that is in the form of a network, and that you can differentiate. So that means you can easily optimize. And if you do that on sequences, that means like you model your sequence as a series of conditional probability distribution, one for each step of your sequence, and you apply some softmax at the end to model like the different possible outputs. That gives you some model that is very flexible and that can learn to produce sequences. And this has been applied, I've seen in the tutorial, has been applied to, although in the tutorial we apply it to images, so it's not really a sequence model. Give the same kind of data, produce drawings, or another application. Actually, that's also something that another guy in the room has worked on, Carol. That was done in Google Zurich. This is smart reply. So you get an email, and automatically the system is suggesting you possible answers to this email, so that you don't have to worry about typing them. Like get someone inviting you to some party or something, and then you have this possible answer that you just have to click on. The idea is you have like some small feedforward neural network that decides whether the email is such that a short answer is appropriate, and then you have a deep recurrent neural network that produces the candidate. You may have seen such applications as well, like image captioning, another application of sequence generation, where you have an image as an input, you try to produce a description of that image as a sequence. There are examples of what the model produced on such images. Let me go, I'm just skimming through these applications because I'm sure you have seen that already. Another application is the machine translation, where in this case you have as an input a text sequence in one language, as an output text in another language, and the system is learning translate. So that's all, going from simple outputs to complex outputs. So this, you bring your big hammer of supervised neural network, and now reinforcement learning is another interesting domain where, if you think about it, the problem doesn't really look like a supervised classification problem upfront, right? You have an agent that is interacting with some environment, gets some observations and reward from the environment, and it performs some action. And usually you want to maximize the expected discounted reward over time that this agent gets. So it's not quite that you are trying to predict y given x, right? But like most of the recent successes in reinforcement learning come from applying this supervised DNN operator to the problem by transforming the problem into a supervised learning problem. One example is when you do value function learning, which means that you're trying to predict given particular states what is the and given policy, what is the expected reward that you will get, and that becomes a supervised learning problem because you perform a lot of experiments and you collect for each state the expected reward that you observe, and you learn that. Another approach is what is called pure learning, where instead of predicting the expected reward in a given state, you predict the expected reward in a given state for a particular action. But basically, it all is based on doing SGD on a parametric model, which is a deep neural network. And you have seen these applications, the Atari games, or now there are applications in robotics as well, data center optimization. All right, so what's next? You may wonder, right? Like, how far can we push this idea of applying supervised learning techniques to various kind of problems? If you think about the, stepping back, like the history of this switch from classical programming to machine learning, what happened is that, in classical programming, what you do is you have some inputs and you want to produce some outputs. So you hire some programmer and you ask the programmer to write a program that, figures out how to process these inputs to produce these outputs. Okay? Now, of course, machine learning is essentially replacing that process by a slightly more generic but more complex process, which involves multiple steps. Instead of that, you say, well, let's label a few examples. Let's collect a few examples of input-output pairs. That's the human labeling aspect. Then let's hire ML experts, and this ML expert will do potentially some feature engineering, figure out what is the right loss function to use, develop a machine learning algorithm. When you apply the whole thing, you will learn how to map inputs to outputs. Right? So we replace this kind of software engineering by new kind of approach to programming. But what deep learning has done essentially is to get rid of that middle box. As I was saying earlier, now with enough data and enough compute power, you can essentially learn your feature, right? But now you may wonder, like, how do we get rid of the other boxes? And that's exactly what the applying that thinking can lead to. I will talk about this in a minute, but so basically, one thing you may want to get rid of is the ML expert. But that means you need other meta experts. Don't worry, your jobs are safe. Well, I'll talk about this. Another thing is you may want to get rid of the loss function or even learn the loss function. That's the idea of generative adversarial network. I'll come back to that. And Ilya already. And then you may also want to get rid of the human labeling because that's also something that is slow and painful. And I also. All right, so let's start with the learning to learn, or automating the learning, the design of the learning algorithm. So currently, we are more or less at this stage where we use a lot of data, a lot of computation, and ML expertise. Ideally, or at least if we want to scale, right? Because you see, there is this immense potential of applying machine learning to many, many different problems. If we want to realize that potential, we need something which involves fewer human experts or fewer human experts. So instead of that, like if we could replace this by data or more data potentially, but more computation by applying this, supervised DNN operator, that would be really powerful. So here are some examples of work that has been done recently in this direction. So one of this is this paper here, where the idea is like you have an architect neural network, which like spits out possible neural network architectures. Right? You have a first neural network that generates, whenever you run it, it generates a potential architecture for neural network. Then you train all the neural networks that it generates for hours, okay? And you look at at the resulting loss of each of these generated neural networks, and you use that as a reinforcement learning signal to improve your architect network over time. And with that, you can basically design architectures so they don't look necessarily very nice and understandable. This is one example of an architecture that was developed for on an image classification task. And you see that you can get to accuracies that are pretty close to the state of the art, but entirely automatically. So that means there is no human that has sat down and designed all the structure. This is another example in a recurrent setup where you are trying to predict, you're trying to do language modeling. And here, this is the classical LSTM cell, like this. What the neural network with this procedure has covered is another cell, which looks a bit more complicated, but performs better. Another direction for automating the search in a way, like, I mean, to some extent, this is really trying to replace like this long and painful process of trying to come up with the next trick by something more automated that's better. Okay? Another such thing, like another painful thing in learning is like the choice of the optimizer. Same thing here, like instead of going from SGD, Adagrad, Adam to whatever else, why don't we optimize the learning rule itself? And this is what has been done, right? Like you see at the top the classical learning rules that people use to practice, and here are all the possible, or at least all the successful learning rules that the neural network has come up with, and see that it found one that is better than the best human designed one. And what is interesting is that it's not just random. Like, I mean, in this case, there was some prior to try and force the rule to be simple so that we can interpret it. And one of the interesting rules that came out of this search is this one, which makes a lot of sense if you interpret it. But G is the gradient, M is the momentum, or like the average of gradients for the last few steps. And what it says is that you take your gradient and you multiply by exponential of the sign of the gradient and sign of momentum. That means if your next gradient step goes in the same direction as the previous gradient step, then you do an even bigger step. And if it goes in the wrong direction or in the opposite direction, then maybe you should slow down a little bit. Makes a lot of sense. And what is interesting is that even with this brute force kind of search, you can discover something that it would have taken some time for a PhD student maybe to come up with exactly that. All right, now moving on to learning the loss. There are lots of problems where there is no obvious loss function to optimize. Say you want to produce images and you want to produce an image that looks good. What does it mean to look good for it? It's very hard to. Or you produce some text. Does this text make sense? And you can't really do backprop on it when you see it. And so you need some alternative way. And the adversarial training, one of the advantages of adversarial training is that it provides a solution to that problem. And again, it's really this operator of, like, you have a problem that is hard to formulate. If you cast it into a supervised learning problem, then it becomes easier. That's what it does. Like in the adversarial training, you can view it as this way, right? That you give me some data that really looks like what you want me to produce, and I will train some network that is trying to discriminate between the data that you gave me from the data that's being generated by the system. Then the harder it is for that network to distinguish between the two, then the more likely what I'm generating is similar to what I want. So it's a very natural way to do it, and it's a very natural way to cast this problem into a supervised learning problem. Of course, not everything is easy. We have heard also from previous talks that in practice, training these kind of two networks that are competing with each other is very. One particular application of that is super resolution, where it's hard to define what is a good-looking high-resolution image. And like this is the original image. You can imagine that it has this downsample, like lower resolution, and these are three different ways of reconstructing that original image. But of course, when you downsample, you lose a lot of information, so you can't really make up for that information. But what you want is not that the reconstructed image matches exactly the initial image, but it has to look like the original. Like, for example, in the color here, when you have this in very low resolution, it's hard to imagine that you can reproduce exactly that shape. But and as you see, you reproduce something that is very different, but from far looks reasonable enough or realistic enough. So that's what this adversarial learning allows you. Now let's move on to getting rid of the human labeling efforts. So as I said before, you have this explosion of computing power, and most of the recent successes come from the fact that we have lots of computing power and lots of labeled data. Now, computing power, as I said, we are producing more and more. Labeled data is still very expensive to produce or to generate, so it really is becoming the bottleneck. we want to go further, we need to reduce the need for label data. And one possible way of doing that, yes, you may have seen this picture in Generalization Gap, where it's saying that the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, and the cherry is reinforcement learning. But anyway, the point is that what we need to solve is this problem of learning a representation that is useful for multiple tasks so that you don't need labels for every task that you solve. And again, how do we transform that question into supervised learning problem? So here are some examples. Again, you have seen that Word2Vec is this idea of you want to build an embedding of words into a vector space. For that, you're trying to convert this problem, which is supervised, right? There is nothing that tells you what is a good embedding word. You should convert that into a supervised learning problem by saying, let me try to predict, for, given a word, given surrounding words, what is the word in the middle. So if you manage to predict, given the words around what is the word in the middle, then that means you have understood something about the words, and you have potentially built a nice semantic embedding. Another approach that's for images, where you take an image and you want to build a system that, given, say, two patches of the image, figures out where they should be placed relative to each other. And if you manage to do that, that means you have understood something about the content, the semantic content of the image, right? Like if you manage to put the cat here, that means you understand that this is a cat here, and this is the face of the cat. Another generic way of doing that is like autoencoders, and again, you can see autoencoders as an attempt to do supervised learning in an unsupervised setup where you don't have labels, but you are trying to, given an input, reconstruct that same input, and the loss is the reconstruction error. You have some constraints on the representation. But that leads to the question of out of battery. Okay. Works. So that leads to the question of how do you define a good representation? I mean, this is by far not a solved problem, and these are just potential directions. Like you could define a representation as a structure that captures the mechanics of the real data that you're trying to model, and you want in particular some properties, some regularity properties. Like one of them is that you can interpolate in a representation space. That if you take two representations of particular instances, and you can draw a path between those two representations such that any point on that path corresponds to a real natural image, let's say, or arithmetic of representation. And combine representations in a way. Here are some examples. So this is an example where you take two images of bedrooms, the one top left and the one at the bottom right. You encode them into your representation space. Then you draw a path in that representation space, like linear, and then you look at what images correspond to each of the points on that path. You see that they all correspond to bedrooms. So you can interpolate from bedroom to bedroom to other bedroom. So that shows that the representation has captured some potential this data set. Another example where you can do this arithmetic on representation with images is where you can take a bunch of images with glasses you can take a person with glasses, a man with glasses, a man without glasses. If you compare, like if you take the representations of these persons in vector space, right? And take the vector that's minus the vector that's plus the vector for the woman, that leads to creating an image that is the person with the glasses, like the woman. All right. So this was to give you a sense of like where this all is going, right? Like we have data, we have computing power, we have lots of people with smart ideas. And the point is, now let's try to apply this successful supervised learning paradigm to as many problems as possible, including problems that exist in machine learning, to make it scale even better and be applicable to even more problems. But that said, there are still lots of real challenges that we're facing when applying machine learning to concrete problems. So I will say a few words about that. So, okay, this is a table that is trying to contrast what happens when you do, machine learning in a research environment versus when you're trying to apply to a particular problem. One difference, which is very important, is that usually when you're doing research, you are kind of free to choose the problem you're working to a large extent, right? Like if your system doesn't work on that data set, well, fine, go find another data set which it might work. Or if images are too hard, just work on text. That's fine. When you're trying to apply, it's kind of a bit different, where the application is coming to you and think, well, we want to solve that problem. And you cannot say, oh, no, image is too hard. Let me focus on text. Right? Another thing is that, like in research setting, we define the metric, and then like everyone fights to get the best system on that particular metric. In practice, a single metric is rarely capturing all the subtleties of the problem. Another aspect is that the data that you're given, usually in a research environment, has been collected already, and that's the data you have to work with. There is nothing else. In an applied setting, you are free to go and find and collect more data potentially. And there is a lot of leeway for improving your system based on collecting more data. That's, in some sense, where you may spend the most of your time finding the right data to solve a problem. And lastly, the algorithm itself that you use is something that, in some sense, that is the thing that you are optimizing if you're in the research setup, because you need your algorithm publishable, new and different. Whereas when you're working on an application, it doesn't matter whether your algorithm is new as long as it works, right? And it's very much constrained by all sorts of different considerations. Let me give you some example of all that, just an idea. Let's take the problem of spam classification. In a research setup, spam classification is often thought of as a text classification problem. You have a piece of text and you have to say whether it's spam or not. In practice, it becomes a very different problem where you have like complex feedback loops depending on how you, if you classify certain emails as spam, then they go into your spam box. So that means the user doesn't see them anymore and doesn't click or label them as spam anymore. So then you have the distribution will shift over time, and so on and so forth. And I'll come to more aspects of that. And so, like going through the list that I was showing you on this table, this notion of no single metric is very important in this case. Depending on the example that you have, like a spam email versus a phishing email, could that be classified the same way? Or spam can have different degrees depending on the user, right? Like some people might consider something that is just like some advertisement, like a spam, and some people may actually want to see this advertisement. You can't, have one size fits all kind of classification. And so you may need some judgment involved, like when you want to apply the system, and like it's not that you will have just one metric and this like error rate is the only thing that you care about. There might be other aspects. Then there might be all sorts of other constraints in real problem, which have to do with you're not just trying to optimize some metric. You also want your classification system to to be fair or to be safe or robust to adversarial examples or robust to distribution shifts and all sorts of other considerations. So that makes it for, in some sense, extra interesting research. And what I'm saying, the reason I'm saying all that is not to tell you that we live in a bubble as researchers. It's more to tell you that if you look at the concrete problems that surface when you try to apply machine learning, there are lots of other interesting research questions to be tackled. I probably skip through that, but that's just to say that fairness, for example, is one of the active research areas around improving the real-life aspects of machine classification. Another one is privacy, because that's yet another thing that you want to build machine learning models in a setup where you have lots of user data, and that user data, you don't want it to be leaked through by by the model. Let me go back to this table. So I was telling you the data is also something that is something that you want to optimize in an applied setup. So of course you all know that you all have heard that the data is never clean, and you spend a lot of time cleaning up your data when you're trying to apply machine. But it's not the only thing that you spend time with doing, right? It's not just cleaning the data; it's also looking for the data that they consume for the time. Let me give you an example. Going back to the spam problem, it turns out that there is a striking difference between when you do spam, like on a classical benchmark, that academic benchmark, where you have a bunch of emails. That's all you have. So you have to process the text. There is no escape. Whereas in most applied setup where you do spam classification, you also have this particular feature, the IP address of the sender of it, which is very hard to fake for a spammer. And they end up using botnets and so on. But still, typically a spammer will send a spammy email, or lots of spammy emails from a single IP address. What that means is, if you know of the rate of spam coming out of the IP address, you can easily determine that from that IP address, if you've seen, like, I don't know, in the last hour, you've seen a certain percentage of spam email coming out, you can pretty much blacklist that IP address, and you will classify 95% of the spam already just with that one. Which also means that if you don't have this feature in your data set, well, good luck, right? You will try to do word spotting, keyword spotting in email, but spammers are smart and they know how to circumvent that and to write Viagra in different ways, and I don't know, with pictures and who knows what. So the point is, having the right data is essential. And even if we have now this super powerful system that can learn the features automatically for free for you, if you don't have this IP address, you don't forge the IP address from the text of the email. That's not possible. Another aspect of that, like going down to the last row of the table regarding algorithms, there is the issue of scale. Sometimes, as I said before, like the algorithm doesn't have to be original. It has to scale. It has to work. It has to satisfy certain constraints. Scale being the most obvious one if you're in the large-scale setup, but there are other constraints, like you want to be able to integrate certain constraints, right? Like you don't want to give all the decisions to your system. You may want to say, well, okay, I'm trusting this classification system to a certain extent, but then in certain situations, I want to be able to override the classification. That's what is called policy layered system. So you need something that can take into account extra constraints. Here I have a long list of other challenges that come up when you're trying to apply machine learning. There are issues around the distribution changes, the way that when you the fact that when you retrain your system over time, it may drift, or the features themselves may drift. The fact that you may need to be able to debug what the system is doing, you want to improve it over time. There are lots of issues, and I don't want to bore you with that, but I think the message is really keep that in mind. It's both something to keep in mind when you do research in machine learning, because it's good to know that not everything is just applying the latest and greatest algorithm. That's one aspect, and the other aspect is there are lots of interesting research challenges and research problems also once you're starting looking at terms of how do we debug these big black boxes that are neural networks, or how do we come up with an interface, for example, of that specifies the expected behavior, right? Because specifying the expected behavior just with throwing training data at your problem, at your system, is not necessarily the simplest way. All right. So now moving on to another topic, the last topic. So I've told you that there are challenges in applying machine learning. Now I want to say that what are the challenges in machine learning research. So, we've seen that whenever you can cast your problem into a supervised learning problem, it's all solved, it all works, it's great. There is nothing to worry about anymore. Problem is we don't understand why that's the case. It's very hard to understand. And this picture that you may have seen in Max Welling's talk actually is problematic. Remember, like if you thought the training error here in blue as a function of the capacity of your model, the test error, you have this effect that the training error goes down, but the test error after some point, if you increase the capacity, goes back up. And the challenge, like theory, is to find this optimal trade-off here where you have like a model that is good enough to fit your data, but not too large so that it doesn't overfit and doesn't go crazy on test data. Problem is, deep learning models, they sit more or less here, or maybe here on this axis of capacity. They have huge capacity, and yet they don't overfit. Why? And there are lots of questions related to that are totally unanswered, and I think those are the questions that want to do machine research, but the question working on. Why are all these things working? Right? Like, so the fact that you have these models with huge capacity and yet they don't overfit, or the fact that we have like super over-parameterized models and they work better than if you add just the right amount of parameters. That's the phenomenon that's also Max Welling presented in the talk, where you can compress to super tiny size the network, but if you try to learn the compressed network, you're doomed. Another thing is like there is regularization for sure. There has to be something like this happening somewhere, but it's not explicit as we used to understand it in like SVMs, where we have this nice norm, the RKHS regularization. And we have like these very weird surfaces with large amount of local minima, and we do SGD and it kind of works. What is that? So this is kind of the state of affairs in terms of the capacity versus generalization trade-off. We don't really understand. PNNs can memorize somehow a lot, or they have huge capacity, so you can memorize pretty much any data set, even if you shuffle the labels that was shown in the paper. But if there is something to discover in that data, they will discover it still, right? They won't just overfit to the particular training data. If there is some structure, they will find it. So now you look into learning theory and you say, well, maybe there is an answer somewhere there. Problem is not really, because this theory just says, well, we can prove results that look like over time, or like as you get more training data, the error will convert to 0 at a certain rate based on the capacity of your model. And you can tune the capacity to the number of training data that you have to get universal consistency, all this stuff. But in practice, we have finite samples, and we have finite capacity models. Like even a deep neural network is not universally consistent, which means that if you increase the number of training data, the error will not converge to 0, unless you also change the size of the network as you. Now, some people have tried to apply some stability ID to understanding of neural networks. There are like these 3 papers that I know of recently that try to do that, but again, it's not completely a satisfactory answer that you get to that, because what happens is you can prove that if you don't do too many gradient steps, you're stable, which means you don't explore too large a region of your parameters. Yes, great. But if you actually, if this is the reason why you generalize, then that doesn't match with the idea that you can reach training error 0 and generalize. Because to reach training error 0, you need to be able to make large, to go through a large portion of your parameter space. So that kind of doesn't add up. There are like in this last paper, there is this idea that, well, the stability is like you have more stability if you start with in a flat region. Like if your initialization puts you in a region of your space which is relatively flat, then you're stable. Well, obviously, like take small steps in that small region, you won't go too far. But again, that doesn't mean that in this region you will generalize more, right? That's more theoretical. And even more, if you try to force stability onto your algorithm, if you want to make the algorithm even more stable, it won't work. Actually, the other way, the other phenomenon will work. Like if you add noise, it works better. So that's really weird. Another thing is, like people are trying to search for answers in the theory of stochastic gradient descent for complex problems. But if you look at what happens in practice, there is this weird effect that if you keep the learning rate constant and then suddenly drop the learning rate, then the training error drops drastically when you reduce your learning rate. And if you drop it too early, you won't converge to the optimal. If you drop it later, you go to an even lower minimum. And so this is really kind of reminding of this idea that, or makes you think of this idea that essentially SGD with this kind of learning rate schedule is like random search, right? Like you have this very complex landscape, and initially you want a large learning rate to explore as much as this landscape as you can. Then once you've explored enough local minima region, you want to pick the best one, and in that best one, you need to have a very small learning rate in a way to find the bottom of it. Right? And people have even tried to actually apply complete random search algorithms, the gradient-based algorithm, and they work pretty well. So again, that's something interesting and far from understood. Another aspect is dropout as a regularization mechanism. Yes, dropout solves all known overfitting problems. That's something that you can keep in mind. Like if your training doesn't work, or if you're overfit, just apply dropout to work. Some extent. And again, that's something that is not really understood. Like explaining it in terms of reducing the capacity, I don't think it's a viable understanding. Explaining it in terms of some Bayesian averaging, I don't think it's an explanation. It's just a rephrasing. It doesn't mean that to rephrase you can understand. I'll come back to that. Yeah, I mentioned this effect of distillation where, like, if you train the large network from the beginning, first, if you try to train and then you compress it, it's better than if you try to train small network directly. So, okay, so what is it that makes all these things work? I think, and I'm not giving you an answer, but I pointing you to some direction here. Like in some sense, instead of trying to understand the magic of the algorithm, let's try to understand the magic of the data. Because really what it is you can think of it as we have found a bunch of areas and problems which have data that is easy to learn, right? We have found, these images actually, they are easy to learn. That's probably why it works. And people have come up with potential hypotheses like, oh, maybe this data lives on some low-dimensional manifold. Maybe, hard to know. And at least one thing that we know is that if this manifold is in a high-dimensional space with few training data, there is no way you can recover that manifold. So it can't be that the system is recovering the manifold and then doing classification of that manifold. There has to be something. Clusters, maybe, but there are lots of data sets where there is no obvious notion of clusters, yet it works well. Hierarchical structure, maybe, and of course, that like these CNNs or deep neural networks, they seem to encode some hierarchical structure, so that might be the direction. Invariances, yeah, the data has lots of invariances, like images, they are in station to a large extent. That might be a reason. But in any case, it can't just be that the relation between your inputs and your output is simple. I think it has to do with the fact that the inputs themselves have a lot of structure. The network is able to use that or to discover that structure to some extent, and use the fact that this structure is related to the labeling function. So, okay, but now let's take another point of view. Imagine that you say, well, and I'm sure lots of you have heard about this kind of statement that, well, we have the perfect theory already. Like, why do we bother? You apply the Bayes rule. People, I mean, if you believe in Bayesianism, say, basically there is no questions about it. That's the way. Why do you even wonder, like, what else could there be? And by the way, all these deep learning business, just a special case of that, because every time you optimize some loss, you can reframe that as a maximum a posteriori estimate within certain model, because you just take the exponential of your loss. Yes, maybe, but I think it still doesn't explain anything. Let me give you an example. Like, you know, when I talk to, I met once like a very convinced patient, and like the answer was, I was asking, but what if your prior is wrong, right? Because you say, well, if you have your prior, apply Bayes rule, done. What if the prior is wrong? Well, it doesn't matter, because if you have enough data, the prior washes away, and you're good, right? The prior doesn't really matter, because eventually the posterior will converge. But isn't that like saying, well, you know, if you look at k-nearest neighbor are universally consistent. What that means is that no matter what is the distance function that you choose on your space, if you have enough data, it will converge to the optimal classifier. Isn't that the same thing as washing away? Yes. So that means, well, if you pick the right distance, great. If you don't, still great. You still converge. So why isn't everyone using k-nearest? Right? I mean, if it just works the same way as Bayes rule or anything, like why don't you pick any random universally consistent algorithm to apply? Well, yes, why? Second thing is, no, but wait. When you do Bayes rule or when you have you know, Bayesian modeling, you have this great thing of uncertainty. And that's amazing, because in practice, that's all you need. Because you can't really trust your prediction. But if I give you the estimate of the confidence, then it's all good. The problem solved. Problem is, even like, don't you, you know, if I give you a model, I give you a probabilistic model, and I say, well, here is the prediction at a certain point x. Would you trust that prediction? No, you would say, hey, show me on the test set how good is that prediction. So you would measure, you know, on the test set accuracy. You would say, okay, test set accuracy is 80%. So yeah, I should trust your predictions only 80% of the time, right? That you would do. So now if I tell you, okay, here is my prediction and here is my confidence, why would you trust the confidence estimate more than the prediction? That's another number I'm pulling out of my hat, right? So same thing. Why don't you measure the, like, you know, maybe the point is the confidence that you get out of the Bayesian model is no different than the prediction itself. It's just another number. If your model is wrong, the confidence will be wrong. So yeah, at least you should measure what is the accuracy of that confidence estimate on the test set, at least, to see whether indeed when you say 80%, it is actually 80% of the time correct or not. So, okay, let me come to the conclusions. And for two aspects, like if you're a practitioner or a researcher, or if you want to be, I think it's, you know, we are living exciting times. I hope I conveyed that through these examples. But there are lots of things that we need to be aware of. As I said, if you want to apply machine learning, there are lots of challenges in doing so, and lots of exciting research problems to be solved if you want to do that and have the maximum impact on society. And as researchers, there are lots of open research questions, right? Like we don't understand much in space, and yet there are lots to be understood. And there is also this point, which is very interesting, that because of this, again, right, like this specific instance that we're living in, there is this connection, this strong connection between this scientific field becoming nature and becoming applicable to lots of different industrial problems, which makes those two fields very connected, like those two domains. And as I say, there is lots of room for a deeper understanding of the phenomena. And I would claim that none of the existing theories or approaches or anything really satisfy or fit the bill. And last point, which is kind of going back to this movie, is that we're still very far from generalized AI. Because in the movie, WarGames, at the end of the movie, the computer, like after having learned to play chess and checkers and whatever, tries to learn to play, I think it's called thermonuclear war. Because in, you know, Cold War era, and the computer tries to figure out like what is the best way to win the war against the Russians. And it tries lots of simulations. Oh, what if we, you know, invade first from this way and then that way and whatever. And at the end, like after playing millions of games, it figures out, oh, turns out that maybe there are games that you just can't win. Maybe you should just even not play, because at the end, everyone loses. And getting to that level of understanding for a machine, right? Like now, okay, the machine is playing Go super well, but I don't think it understands what it even means to play Go. And that's a bit sad to think about it. And that means we're still very far from true AI. And for and one thing that we're actually working on in Zurich is trying to define what it means to have a notion of common sense in computer and how to learn this. Anyway, is that the necessary slides about hiring at Google? So sorry for that, but this is just giving you a sense of all the areas that of research that we're doing, and here are all the possible positions we have. And I'm happy to tell you more after that. Thank you. We have time for questions.
Thank you for the talk. When you were starting the talk, you mentioned some challenges and how to get them. You presented this paper on searching for neural architecture. So from what I remember there, it said that how it searched for architecture, it used huge computational resources. Something around 800 GPUs is what it used. Right. So I mean, in practice, I mean, we would want machine learning scalable to have people access to, and people won't have access to such large computational resources. So do you think learning the structure itself, so something like what's done arithmetic circuits, also be a way to go to make it scalable, so that you, from the data, you learn the structure, which essentially helps you in solving.
Yes, I think the brute force way that I presented, of course, you need to be able to afford using that amount of power. As I said in the beginning, like as Google, we are making a lot of this power available to researchers for free, right? But that doesn't completely solve the problem. And so I think it's definitely worth investigating other areas or other directions for solving that problem, of figuring out what is the right building block or the right layer or the right connection pattern for so yeah, definitely, I think as we have seen so far, it's an art more than a science, designing the right learning. That has to change, right? Like if you want to be able to apply it at a broader scale or like to more problems, we need to find techniques for automating that. And some techniques will, like, it's worth trying to do it like brute force exploration, brute force search, but it's also good to still, try to inspect the data, try to understand better what is the connection between the structure of the data and the structure of the network. That might take further than maybe search space is too big to do anything. Although in some cases we've seen some successes, but it doesn't completely solve the problem.
Okay. So you mentioned something about this feedback in the part of your talk. Now, as we are moving forward with deploying more and more of these deep learnings in different areas, apparently most of the data that we collect, learn, and train these models are actually data generated by some other deep learning or computer-generated program instead of the human data that we are mostly using nowadays for training these models. Do you think that there is an implication of these kind of highly connected feedback loops that basically connect companies, countries, economies, and do you think that it would make it kind of fragile in terms of potential perturbation for miscalculations or changes?
Well, I don't think we are yet at the point where there is such an interconnected set of machine learning systems that feed into each other. For now, all machine learning systems are fairly isolated. They just produce, I don't know, pattern classification on the one hand, or I don't ads targeting, or feed ranking, so which are slightly separate. So I don't see that.
Yeah, but there will be still.
Or will it
Beautiful.
Did someone say Joshua? That's the name of it. Okay. Yeah, going back to the question, it's. I think we are far from that. What we are seeing still is, I mean, these feedback loops at a smaller scale, where indeed, because the data that you're showing to the user is the result of some machine system, then you don't show the same data. Like the distribution of it is determined by your machine system, so you don't get feedback in the same way over time, and that means your machine system may degrade if you don't get them to that, and you need to introduce some sort of exploration.
So as a person who, so you actually explained a little bit about that in your slides, but as a person who moved from statistical learning theory or machine learning theory to practice, some more applied. So can you explain a little bit about the challenges during this transition, going from theory to application?
Well, it's been a process. No, I think maybe maybe it's a bit personal in some sense, but I think I found it relatively easy to switch from one to the other, because I was always driven by the desire to understand, whether like understand theoretically or understand like really what makes it work and fixing it work, kind of the same process. I think the bottom line is really, if you want to, I mean, if you're really to tackle a problem and really focus on the problem rather than on the method or on the approach or whatever, you always find it. Right? And like you say, I'm going to work on the theoretical problem. What matters is that you solve the problem. Say I'm going to work on this practical problem. What matters is to solve the problem, not that you apply the A to that problem. Or, yeah. So yes, that would be my advice. Just focus on the problem.
Thank you for the talk. I think part of it was devoted to maybe comparing industry to academia. My question would be, what about when it comes to teamwork? As in, I think there are definitely differences, and we'll be happy to know about your experience.
So we may be drifting a bit away from the content of the talk, but try to answer that. One sense, there is, like, incentives are different. And there is one somewhat damaging incentive, I think, in academia, which is that like PhD students need to have their own topic and their own set of papers where they are first authors and so on, which reduces the incentive to work together as a team, which is something that is not the case in industry. Then you can work on bigger problems with more people together. That would be one difference. But apart from that, I mean, there are lots of other differences, of course, positive and negative points on both sides. I think now it's both are very close in terms of excitingness of the kind of work that you can do, and like research topics are very similar in both cases. Fairly balanced.
Okay, so let's move on to the coffee break, and then afterwards to the practicals. Please join me in thanking Olivier Francois.